the light version of Chinese Remainder Theorem. So in Chinese Remainder Theorem, what we do is we solve for 2. The theorem, what does the theorem tell us? We will look at that. The theorem, what does the theorem actually tell us? The theorem, one example. I will only do one example in this video. Hello everyone, welcome to this new video, and this is going to be a very interesting video. We are going to do the light version of Chinese Remainder Theorem. Now, this Chinese Remainder Theorem is quite useful in solving congruency equations, right? You must remember that we once solved, when we were doing congruency, we solved something 5x is congruent to 1 mod 12, I suppose. This is what we solved. And the solution was, x congruent to, the solution was x congruent to 5, I think. So, this was a linear equation and we were solving linear stuff. So, we wrote this is congruent to 25 mod 12 and from there we get this. So, in Chinese Remainder Theorem, what we do is we solve for 2 such linear equations. So, it's like solving simultaneous congruency equations looking like this. The theorem, what does the theorem tell us? We will look at that later, but what do we actually deal with is this. To solve for simultaneous congruencies, x is congruent to a1 mod n1 and x is congruent to a2 mod n2. So, if x satisfies both the congruencies together simultaneously, that's what the word simultaneous means, right? Same time. That's what the word means. Now, if that happens simultaneously, okay, why is this important? So, it's like one example we can take is x is congruent to 1 mod 3 and x is also congruent to 1 mod 5. Okay, now in this case the congruency is 1 1. So here the solution appears to be very, very simple. If you take x is simply 1, it works for both. Right? What could be the next? What could be the next one? Think about it. So it has to be 1 mod 3 and 1 mod 5. So if you think enough, the next will be 16. And the next of that would be 31 and so on, and I hope you see a pattern there. Actually, Chinese Remainder Theorem is much more than this. It generalizes till x is congruent to ak mod nk. Okay, Chinese Remainder Theorem talks about any number of congruencies, any number of simultaneous congruency. So we will do for IOQM particularly, we will only need till 2. So we will only deal with that, and this is going to be relatively a very short video, purely for your information, right? And interest. So the theorem, what does the theorem actually tell us? The theorem only tells us that there will be a unique solution. A unique solution less than or equal to n1 n2 exists whenever the GCD is 1. If the GCD is 1, there will be at least one unique solution. That's it. That's what the theorem tells. The theorem tells us about the existence and the uniqueness given under certain condition, right? So it is like solving 2 linear equations. So we often look at a1x plus a2y plus a3 is 0 and b1x plus b2y plus b3. I know this is not the standard way of writing it, but I am just telling you, we solve this and there are certain conditions. Solution exists if, what is the condition? That the determinant a1, a2, b1, b2 is non-zero, right? That's what the solution tells us. Maybe I'll erase this and write again. if A1, A2, B1, B2 is non-zero. If this is non-zero, only then the solution will exist. That's what the linear equations tell us. So for this one, x congruent to A1 mod N1 and x congruent to A2 mod N2, the solution exists whenever the GCD is 1. Solution exists if and only if GCD of N1 and 2 is 1. Okay, it's not only if, it's only if, right? Okay. Now, let's look at one example. I will only do one example in this video, but I will do it in two different methods. Now, according to the theorem, since GCD of 5 and 7 is 1, implies solution will exist. Right? So the solution will exist. So we have to kind of look at and unique, and there will be and unique number will be there less than or equal to, in this case, 5 into 7. So let us try to hunt down one number 5 such that it is like this, right? So let us first of all list down all the possible numbers. So for x is congruent to 3 mod 5. So how will the numbers look? There is 3, there is 5, what the hell, what am I doing? What is the next number? We add 5, so it will be 8, it will be 13, it will be 18, 23, 28, 33, 38. Okay, we have crossed, this is 35, right? So we only have to check before this. And x is congruent to 2 mod 7. This tells us that it is 2, 9. Yeah, I'm adding another 7, so it's as 16. I'm adding another 7, 23. I'm adding 7, 30. I'm adding 7, 37. So it has to be before that. Oh, clearly 23 is a common solution. So we definitely have x is equal to 23 satisfies both. Furthermore, the theorem actually tells you that whenever x is congruent to 23 mod 35, it is a possible solution. So I must actually extend it that when there will be a solution, and the solution if x is equal to a less than or equal to n1 and 2 is a solution, then general solution is x congruent to a mod n1 n2. Right, this is the normal solution. In this case, what do you find the solution to be? It is simply x is congruent to 1 mod 15. Isn't it? As simple as that. I want you to check. Now the homework will be that check that this works. Right, I'll change the color so that you get serious about it. Check. Yeah. Sure. Now, there is another way to do it. Method 2. Method 2 will be that, again, what was the question? Question was x is congruent to 3 mod 5 and x is congruent to 2 mod. Now, okay, let's see. X is congruent to 3 mod 5 tells us that x is of the form 3 plus 5k, right? Now you put this in the second one. That implies 3 plus 5k should be congruent to 2 mod 7. That implies 5k is congruent to minus 1 mod 7, which is congruent to 6 mod 7. So we want to find k such that 5k is 6 mod 7. Now we have done something like that before, right? We have done something like that before. Let's try to utilize that. So we want to definitely 5 comma k, 5 comma 7, GCD is 1. So I want to find a multiple of 7 to add to 6 so that it is a multiple of 5, so that I can cancel out 5, right? So 5k can be 6 plus 14, right? Mod 7. So that should imply 5k is congruent to what is that? 20 mod 7. So that should imply k is congruent to 4 mod 7. Okay, right? Now whenever k is 4 mod 7, okay. So tell me one thing, look at this. K is 4 mod 7. That should imply 5k is also 4 mod 7. But that tells me a little bit more. With 5k, I can actually extend this to mod 35. Isn't it, guys? Like, just think about it. So I can actually say 5k is congruent to 4 mod 35. Why? K is congruent to 4 mod 7 means k is equal to 4 plus 7 into L. 5k is equal to 4 into 5 is there, but it's also 7 into 5 into L. So what is, okay. I have to do 20 here. This has to be 20. This is not 4, of course not. Right? It has to be 20. I have to multiply 5. It is, first of all, it is always 5k is 20 mod 7. Okay, that's my bad. (20 mod 7), but it is also 20 mod 35. It is anyways, it is 25 plus 35. So I can say 5k is congruent to 20 plus 35, or congruent to mod 35, right? 20 mod 35. And my x was 3 plus 5k, right? That implies x is congruent to 3 plus this, 23 mod 35, right? And less than 35, there is only one solution, which is 23. So that's what Chinese remainder theorem tells you, that there will be a unique solution whenever the GCD of the modular number is 1. So yeah, that's all I wanted to cover. So let me know if you found that very, very useful. And I want to remind you of something, that AX is congruent to B mod n. A solution will exist whenever GCD of A comma n is 1. Okay. So that is really important to note. And in fact, you can almost write it like x is equal to A inverse B mod n. Now what will be this A inverse? A inverse will be a number, let's say I have a number A naught such that A naught into A is congruent to 1 mod n. Is this possible? If A is this, then there must exist A naught such that the GCD of A naught and n is also 1, and A naught A is congruent to 1 mod n. Right? This is a fact. I mean, I want you to think about this. The proof we will discuss later when I'll do Euler's totient function, which is a bit advanced, right? It is related to Fermat's little theorem. We will cover that. Don't worry. But I just want you to think. This is like thought provocation, right? Array. Thought provoker. I want your thoughts to be provoked. Then I will call this A naught to be A inverse mod n. Right? So think about it. For example, which we did, 5x is congruent to anything, 2 mod 7 or 4 mod 7. Was it 4 or 6 something, right? It doesn't matter actually, because with 5 and 7 there will be a number multiplied to 5 such that it is 1 mod 7. Will there be? Always. Think about it. What could that number be? If I multiply 5 with 3, that's 15, and that is congruent to 1 mod 7. So if I multiply 3, I have 15x is congruent to 12 mod 7, and you see that 15 is nothing but 1 in the world of 7. So this will be x is congruent to 12 mod 7. So this idea will help you. This idea will help you solve any equation of any congruency of the form Ax is mod n, right? Whenever A comma n is 1, find A naught such that A naught A is congruent to 1 mod n, right? So this is how you solve it. This becomes very, very easy, isn't it? Do you want another example? I can give you another example. So I will again solve for 7x congruent to 3 mod 8. Now 7 and 8 is definitely, oh, here 7 itself is 1, 7 is minus 1 mod 8, so it's fine. So I want to solve for this. So there must exist a naught such that 7 a naught is 1 mod 8. Is that possible? Think about it. So if I take 7 sevens are actually, if I take a naught to be 7 itself, then 7 sevens are, it works, right? 49 is congruent to 8. Yeah, that becomes easy. So you see, it is kind of easy. It's always possible. I can take another example. So you just multiply 7 here. So 49x is congruent to 21 mod 8, right? So x is congruent to 21 mod 8, which is, you can take out 16. So it will be 5 mod 8. So you can take another example. Last one which we can do is 13x congruent to 1 mod 7. Okay, that is again easy, I think. That's again easy because 13 is minus 1 mod 7, right? So it's easy, but let's not take 7 then. Let me take 5, right? 5 will be good. So how do I solve for that? So 13 is 3 mod 5. I want to multiply something such that it is 1 mod 5. So I want to multiply x such that 3x is 1 mod 5. So how is that possible? So I want it to be 1 plus 5k type. So, you know, you're essentially building it to some (5k) has plus 1 has to be a multiple of 3. So if I take 20, k to be 4, it will work. It's congruent to 21 mod 5. So x is congruent to 7 mod 5. So I have to multiply 7. So x is again congruent to 7 mod 5. So my point is this statement is my important point. I hope you understood that. So that's all for today. Meet you in the next video. I hope you got something new from this video. Like, I wanted to make it as interesting as possible. This is like super cool for me. Okay, so stay tuned. Take care. Goodbye. Tata.